So last class we asked the question, what do we need to fly? And it turns out that for a turbojet engine, what we want is thrust, because thrust lets the wing on an airplane cut through the air in a way that gives us lift. And lift is what keeps that plane up in the air. So we started to talk about these Brayton cycles. We remember that we're looking at these cycles from the perspective of someone standing on the wing of the airplane. So even if the air is still, our moving frame of reference means that we feel the incoming air whipping past our face. So there's always some kinetic energy going into the diffuser. Well, the purpose of this cycle is to maximize the thrust power. And to do that, we want to get as much velocity coming out the nozzle of our turbojet as we can. So we're trying to maximize V out here. This is different than all the other heat engines we've talked about, where we're trying to maximize the net power per unit heat coming into the system. Now at the core, or the center of our turbojet engine, is a Brayton cycle. We have a compressor, a combustor, and a turbine, and our working fluid is air. If I'm using imperial units, the equations look similar, but they're a little bit different. Remember, if the kinetic energy terms stick around, I've got to divide by GC, because that will give me the right quantity. And even after that, I still have to watch the units, because these will probably be in foot-pounds per pound mass instead of BTU per pound mass. Just like in the metric system problem, if I'm going to keep that kinetic energy term as VA squared over 2, I'll probably get joules per kilogram instead of kilojoules per kilogram. If I'm trying to characterize the turbojet, it looks a little bit different than the thermal efficiency for a Rankine cycle or a Brayton cycle or an internal combustion engine, because it's not mechanical power that I'm interested in, it's thrust power. Now, we're never going to ask you this on an exam, and it's not in the textbook, but it's helpful to remember that the purpose of this jet is to maximize the velocity at the outlet of the nozzle. This equation looks a little bit different if we're using imperial units, because again, we have to divide by GC. So, we've learned a little bit about turbojets, but now we want to go through and do a turbojet problem. So this is what the turbojet problem looks like. It gives us this sketch of what a turbojet looks like, so we know all the different components. It gives us a TS diagram, but we should know how to draw this TS diagram because we might need to on an exam. Note that this is not the TS diagram from this particular problem, because the temperatures here are in Rankine, but the temperatures in our problem are in Kelvin. So we're told the temperature and the pressure at the inlet of the diffuser. We're told the maximum temperature, the temperature at state 3, and we're told the pressure at state 5. Notice that the pressure at the inlet of the diffuser is the same as the pressure at the outlet of the nozzle. This is because both these ports touch atmospheric pressure, so they have to be whatever the pressure is in the atmosphere. We're also told here that the velocity of the jet is 220 meters per second. We're given CP for air, so we can do this problem as constant specific heat, although I'll do it both as constant and variable specific heat. And we're told the pressure-compressor ratio as we go from state 1 to state 2. Notice when we look at this TS diagram that the pressure at state 1 is not the same as the pressure at state 4. So unlike a normal Brayton cycle where we have the same pressure ratio across the compressor and the turbine will not go the same pressure ratio, because here we're only running this so that our backwork ratio is 1. So we'll go to a different state 4 than we'd maybe be used to seeing if this was a normal Brayton cycle. We're asked to fill in the temperature and pressure data on my state table. So basically we'll fix all the states throughout our whole problem, even though we're not given all that much information to begin with. We'll ask to find the heat transfer in and the velocity at the exit of the nozzle. So how do we do this problem? If you guessed, we'll do the first law on all the components, then you're correct. You're used to being in thermodynamics class. First, we'll look at the diffuser. The purpose of the diffuser is to turn as much of this kinetic energy as we can, and we'll assume we take all of the kinetic energy and use it to increase the enthalpy as we go from state A to state 1. To do that, we'll be armed with the first law. We'll assume that we're at steady state, that this diffuser has one inlet and one outlet. We'll neglect the change in the potential energy. We'll say that the diffuser is both adiabatic and passive. And we'll say that the velocity at the exit of the diffuser, that's the port that touches our Brayton cycle, is equal to 0. So the kinetic energy, once we're inside the engine, we're going to assume that it doesn't matter. So now I've got an expression. H1 is equal to HA plus VA squared over 2. Right? We're only dividing by 2 here because this is a metric problem. I can solve this problem either with constant specific heats or with variable specific heats. On an exam, we would tell you which way to do it, but I'll show you how to do this both ways. First here, we'll use a cold air standard analysis where we assume that the specific heat is constant. Here, we know that we'll never find the individual H's. Instead, we'll assume that delta H is equal to Cp times delta T. But that means that I'm going to have to find these temperatures. It also means there's a kinetic energy term in this equation, right? Anytime I have a kinetic energy term, I've got to be worried about the units. This is true in metric and it's true in imperial. So here, because my velocity is in meters per second, this term is going to be in joules per kilogram, but I want it to be in kilojoules per kilogram. So I'll change this equation around a little bit and divide not by 2, but by 2,000, because I know that there's 1,000 joules in a kilojoule. Now, I know Cp, I don't know T1, I do know Ta, and I do know Va. So I can use this expression to find the temperature at state 1. So now I know the temperature at the exit of the diffuser, which is the inlet to my compressor. I can do a similar thing if I'm using variable specific heat, but now I'm going to actually find these enthalpies. In this case, I was given the temperature at state A. So I can look on table A22 because my working fluid is air, and I can find that if the temperature is 230 degrees Kelvin, then the specific enthalpy is 230.02 kilojoules per kilogram. Again, I have to divide this velocity term by 1,000 to get to kilojoules per kilogram, so I can add apples to apples here. When I do this, I get that H1 is 254.02 kilojoules per kilogram. When I look on my table, I can interpolate back and find that PR, the reduced pressure, is 0.776, and that T1 here is about 254 degrees Kelvin. So here I agree pretty well when I get to T1, no matter if I'm using the variable specific heat and the constant specific heat. Let's see if that continues throughout the problem. I also want to be able to find the pressure at the exit of the diffuser. So here I'm going to assume that this process through the diffuser is isentropic. That means if I have a cold air standard analysis, I'm going to look for an expression with K in the exponent that relates the ratio of temperatures to the ratio of pressures. Notice these are not delta T's, so I'm going to have my temperature in Kelvin and not Celsius. Here I know the temperature ratio because I just figured that out, and I want to find P1. So I can use this expression to find P1, and in this case, P1 is just under 37 kilopascals. If I'm using a variable specific heat analysis, I can't use this equation with K in the exponent because K is Cp over Cv, and Cp and Cv are changing. So instead, I use that the ratio of the pressures is equal to the ratio of the reduced pressures. I've already found PR1 from the last part of the problem, so now I can find P1 is equal to PA multiplied by PR1 divided by PRA. I could find PRA by interpolating on table A22 because I was given the temperature at state A at the beginning of the problem. In this case, again, I see a similar pressure of 36.9 kilopascals. So now I'm through my diffuser and I'm going into my Brayton cycle. First, I'm going to look at the compressor. For the compressor, I'm going to make the assumptions that I usually make. That we're steady state, one inlet and one outlet. We're going to neglect kinetic energy. We're going to neglect the changes in potential energy. We're going to say that the compressor is adiabatic and that there's no friction losses or heat losses anywhere between our components in the Brayton cycle. When I do that, I get that the compressor power is equal to m dot through the compressor multiplied by h in minus h out, or h1 minus h2, and I'm expecting this compressor power to be negative. If I'm using a cold air standard analysis, I'm never going to find the specific enthalpies. Instead, I'll see that W dot is going to be Cp times T1 minus T2. Notice that this is lowercase w dot, so I've divided the equation on both sides by m dot. I don't know this specific power. I do know Cp, I do know T1, but I don't know T2. So I have to assume that the compressor is isentropic. If the compressor is isentropic, then I can use this expression with K in the exponent. I would do this even if I was told an isentropic efficiency for the compressor, because first I'd have to find the isentropic outlet, and then I'd use the isentropic efficiency to find the real outlet. In this case, I don't have an isentropic efficiency, so I'm only going to figure out what's going to happen when I have an ideal compressor and an ideal turbine. I'm told the compressor pressure ratio, P2 over P1, is equal to 11, so I can find P2. I put that into my equation, and I can see that T2, if I use this expression, is 504.3 Kelvin. If I was assuming that the specific heat was variable and that the compressor was isentropic, then I would use this expression, that the ratio of pressures across my compressor would be equal to the ratio of reduced pressures, which is equal to R, my compressor pressure ratio, which is 11. I've found PR1, and I know P2 over P1, so I can find PR2 as about 8.5. Now, I take that value, PR is equal to 8.5, and I look on table A22. I interpolate, and I find that H2 is approximately 505.1 kilojoules per kilogram, and that T2 is approximately 502. Notice there is a little bit of disagreement between T2 when I have a variable specific heat and T2 when I have a constant specific heat. Next up, we're going to solve the combustor. The assumptions we'll make here are that the combustor is at steady state, that it's got one inlet and one outlet, that we can neglect changes in kinetic and potential energy, and that it's a passive system. Again, we're assuming no frictional losses or heat losses throughout the system. So I get this equation that Q dot in is equal to m dot times H out minus H in. If this is a constant specific heat problem, then if I divide both sides by m dot and I assume that delta H is Cp times delta T, I get this expression here. I don't know little q dot, but I do know Cp, I do know T3, and I do know T2, because here I was told what the maximum temperature in the engine was. In this case, the maximum temperature occurs at T3. I put all this information into my calculator, and I find that Q dot in the combustor is 895.7 kilojoules per kilogram. But I know that the mass flow rate is 25 kilograms per second, so I can multiply this whole thing by 25 kilojoules per kilogram. I'm going to watch my units. The kilograms are going to cancel out, and I'll get kilojoules per second, which is kilowatts. And I see that the heat that enters the system, or the rate of heat transfer into the combustor, is 22,392.5 kilowatts. I can do this by assuming variable specific heat because I know that T3 is 1400 Kelvin. I interpolate on table A22 to find H3 and PR3. When I do that, I can put that into this equation because now I know H3 and I knew H2 from before, so I can put that into my system, multiply by 25, and when I do that, I find that the heat transfer rate into the combustor is 25,258. Notice that there's an 11% difference between these two numbers, and that's because we're assuming that specific heats are constant on the right-hand side here. If I had to pick which one of these answers I trust more, it's always going to be the variable specific heat analysis because I've made one fewer assumption. And this assumption that specific heat is constant gets worse as our delta T's get bigger. And here we're talking about a delta T of almost 900 degrees. So now we're through the diffuser, the compressor, and the combustor. The next thing we want to do is solve the turbine. The trick to these turbojet problems, or at least one of the tricks, is that we have to remember that the backwork ratio is equal to 1, or that the turbine power has the same magnitude but the opposite sign as the compressor power. So for the turbine, I'll make the normal assumptions: steady state, one inlet, one outlet, no change in kinetic and potential energy, that the system is adiabatic and we don't have friction and heat losses throughout the problem. Now we're going to find that the turbine power is m dot through the turbine times h in minus h out. This is going to be h3 minus h4. But I know that this has to be equal in magnitude to the compressor power, which is going to be m dot times h in minus h out. But because they're equal in magnitude and opposite in sign, I multiply the compressor power here by -1. If I'm doing a cold air standard analysis, I see that all of these components are at steady state with one inlet and one outlet, so the mass flow rate through the turbine is equal to the mass flow rate through the compressor. I also am assuming that delta H is Cp times delta T, so I pull that out. I can also cancel out the Cp's on both sides, and I can use this expression to find T4. T4 in this case is just under 1,150. This is isentropic, just like the diffuser. So if I'm trying to find the pressure at state 4, I can use this isentropic relationship for ideal gases with constant specific heat. This is 1 with K in the exponent. I can use this to find the pressure at state 4. Here I find that P4 is 204 kilopascals. Notice that the ratio of pressures across the turbine is not the same as the ratio of pressures across the compressor, because this turbine doesn't exhaust to the environment, it exhausts to the inlet of the nozzle. And the purpose of the turbine is only to run the compressor. So we used the fact that the backwork ratio here was 1. We'll do the same thing with the variable specific heat analysis, but this time we actually have to find the specific enthalpies. I can arrange my expression to isolate for H4, but I know H1, 2, and 3, so here I see that H4 is 1,264.3 kilojoules per kilogram. Anytime I know any of these pieces of information on table A22, I can find the rest of them, and here PR4 is 228.9. Because I know this is isentropic, I can use the ratio of the reduced pressures to be equal to the ratio of the pressures. So I find that P4 is 206.2 kilopascals. And I interpolate from table A22 to find that T4 is 1,188.5 degrees Kelvin. Notice again, the temperatures are diverging here, but that's because in this case, we're assuming that the specific heat is variable, and here we've assumed that the specific heat is constant. So now we're through everything but the nozzle. So I've got one more first law analysis to do here. And the purpose of the nozzle is to maximize the velocity at the outlet. For the nozzle, I'll assume that it's at steady state, one inlet, one outlet, no change in potential energy, adiabatic and passive, and I'm going to assume that the kinetic energy term, or the velocity that's touching the Brayton cycle, is equal to 0. In this case, that's the velocity at the inlet to my nozzle. Remember, I need to have kinetic energy at the exit of my nozzle because that's kind of the purpose of the whole cycle. So now I can see that V5 over 2 is equal to H4 minus H5. But I got to make sure my units are right. So I notice that if I only divide by 2, that kinetic energy term would be joules per kilogram. So I divide by 2,000 to get kilojoules per kilogram. And now the units on the left-hand side and the right-hand side of my equation agree with each other. I don't know V5, but I also don't know T5. So I have one equation and two unknowns. So now I'm going to have to use the idea that this nozzle is going to be isentropic. So now to find T5, I can use this expression with K in the exponent that relates the ratio of the temperatures to the ratio of the pressures. Now I found P4 in the previous part of the problem. I know that P5 is going to be the same as P at the inlet, that's PA. I put all this information in my calculator, and now I find that T5 is 638.4. And once I have T5, then I can use that information to find V5, and I find that V5 in my moving frame of reference is 1011.4 meters per second. And if I change that back to my stationary frame of reference, I have to take V5 and subtract VA, which is the velocity of the plane or the jet engine, if I assume that the air is still. After I do that, I see that velocity at state 5 is 791.4 meters per second. I do a similar process for my variable specific heat analysis, but here I use a different isentropic relationship because I can't use the expression with K in the exponent because that assumes that the specific heats are constant. So instead, I use that the ratio of pressures is equal to the ratio of the reduced pressures. Here, I know P5 because that's the same as PA. I know P4 because I found that at the last state. I know PR4, which I also found by interpolating at the exit of the turbine. So the only thing here I don't know is PR5. So once I find that, then I can put that information into table A22. I can interpolate and find that H5 is 714 kilojoules per kilogram. I put that back into my equation up here, and I solve for the velocity at 5, and I see that the velocity in my moving frame of reference is just under 1,050 meters per second. When I convert back to the stationary frame of reference, I find a velocity of 829.1 meters per second. So, for my cold air standard analysis, if I wanted to fill in my whole state table, I'm only going to fill in information for the temperatures and the pressures. When I do that, I found that the velocity at the exit was 1011.4 meters per second. For the variable specific heat analysis, I found all the specific enthalpies. I put those into my table, and I found that the velocity at the exit was 1049.1 meters per second. The other thing that I can find in this problem is the thermal efficiency. Now, we're probably never going to ask you this on an exam because, again, it's not material that's covered in the textbook. But just for interest's sake, we can calculate it. We know that the top term, again, needs to be divided by 1,000 in order to get the right units. So when I put information in here, I find that my thermal efficiency in this case, so how much of that heat transfer rate into the combustor gets turned into thrust power, and we see that just under 25% of that heat transfer rate becomes thrust in if we're assuming constant specific heat. Now we know that the variable specific heat analysis is more accurate, and in that case we get that just under 23% of that heat transfer rate into the engine at the combustor became thrust power. So these numbers agree to within about 10%. So you can see that there is a cost in terms of accuracy for assuming this constant specific heat. But we're still in the same ballpark, and the analysis actually took a little bit less effort over here when we were using constant specific heat because we didn't have to do any interpolation on table A22. So with that, we've finished with turbojet engines. We've also finished with cycle analyses of heat engines. We have 2 more lectures left, and we're going to use those to understand how we can use vapor compression, refrigeration, and heat pumps. What we'll find in those cycles is that they're almost like Rankine cycles that run in reverse, and we'll also see an interesting new way of fixing states where we can find things like specific enthalpy graphically on a chart that's provided by the manufacturer. So that's it for today. I'll see you again next time on Thermodynamics.